Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. Very good day. Salam sejahtera. So welcome to Parametric Modeling and Analysis. And today we are going to discuss the introduction to CFD. So my name is Anas Abdul Rahman and I'll be your instructor for this module. So before we begin, a couple of notes. So we'll start our lab module on week 8 until week 10, and then followed by the midterm break on week 11. So on week 8, we're going to start the meshing laboratory, followed by the simulation analysis. And during week 9, your first lab report is due for meshing. And on week 10, you're going to have your lab test number 2, as well as the submission of the lab report for simulation and analysis, which is your second lab report. Okay. A couple of notes. First one, it's important that everyone here attend the lab according to your assigned group. We want to manage the attendance so that it's not too crowded in one lab and not the other. And it is also important that you guys join the Google Classroom. It is also very important that you guys have a look at the detail of submission for your lab report. In the e-learning platform, I have mentioned that submission for lab report must be done using two platforms. The first one using e-learning platform and the other one using Google Classroom. So the same reports, but two different platforms. All right. So why is it important for today's lesson to learn about CFD? I'm pretty sure that most of you guys have seen lots of figures or diagrams or photos that looks like this, the one that we are seeing here on the screen right now. Okay, so but do we really understand the meaning of the figures and the color? What does it represent basically? All right, so a little bit of quotation from James Clerk Maxwell, a famous researcher and scientist. So he said that all the mathematical sciences are founded on relations between physical laws and laws of number. So that the aim of exact science is to reduce the problems of nature to the determination of quantities by operation of numbers. So what does it mean basically? So basically, if you want to study something, okay, pretty much everything that we are learning right now can be basically divided or simplified by laws of numbers, meaning that numerical equations. So that's what these scientists said basically, and that's what is CFD basically. That's what we're going to have a look. Okay. All right. So if you look over here, this is an example of application of CFD and why it is important as a future engineers, you have the skills required to do a basic modeling. Okay, we don't expect you guys in this short 3 weeks period to be a master or be an expert in CFD, but at least you get some idea of what CFD is and how it can be used, especially for your FYP later on. Okay, so this is an example of engine valve, okay, intake or exhaust valve in your engine, where we can study the behavior of the fluid, of the phenomena of the situation that is happening at that moment, and how we basically use the information to improve the engine efficiency, for example. Okay. Second example, this is a tidal turbine. So instead of wind turbine, where you have a turbine on the land, so now you have turbine under the ocean. So we can study the wake generation or the vortex generated from the tip of the turbine of the blades and how it impacts the subsequent deployment of turbine behind the first one. And this is another example, which is a natural phenomena called von Karman vortex, where an object that is being um, located at a certain location faced by the incoming fluid. Okay, so it can be water, it can be air, and the characteristic of the wake is basically the fluid behavior behind an obstacle. So due to the conservation of mass, conservation of momentum, and conservation of energy, and that's what we are looking at right now here on the screen. So this is an example of what CFD can achieve basically. So we want to replicate the natural phenomena as accurate as possible. Okay, but there is something very, very important in computer science, the jargon, okay, or terminology that is called garbage in, garbage out. The thing about tools, especially computer tools or CFD tools, is that the output of the tools or the software is highly dependent on the input. And the input here is basically from the user. So if the user basically doesn't know what he or she is doing, okay, so the garbage, okay, the input is a garbage, meaning that just a compilation or a set of data that doesn't make any sense to the user, then the output from the software or from the tools is going to be garbage as well. Okay, so that's the the importance of understanding the term garbage in, garbage out. So the tools is only as accurate as the experience or the knowledge from the user. Okay. So to summarize what CFD is, basically it means uh, computational transport phenomena. So it's basically trying to replicate what is happening in the real life into a numerical model. So it involves fluid dynamics, heat transfer, mass transfer, or any other processes that involve transport phenomena. And more importantly, we are dealing with fluid dynamics. So that's, I think, quite important that we have a basic understanding of fluid dynamics. Okay, I'm pretty sure all of you guys have taken fluid dynamics, so it helps us to have some background before we dive further. All right. Okay, so if you have taken fluid dynamics, then I'm pretty sure you guys are quite familiar with this equation, Navier-Stokes equations. So any fluid phenomena can be solved or can be dealt with by using Navier-Stokes equation, and this is the main equations behind the CFD software or CFD tools that you are going to use in the lab. Okay, so in conclusion, or in a sense, this is basically CFD. The beautiful figures, diagrams, or output that you have from your tools, let's say NCs, okay, for our class, the behind the scene or behind the software, okay, how you get those beautiful diagrams or colors are due to the equations, basically. So there are mathematical equations that are being solved in order for you to get the nice figures as you are seeing right now on the screen. Okay, so I hope at this point you guys understand the beautiful figures, uh, basically something that is visually appealing that you have uh, on your paper or from the papers that you are reading. It all came out from the mathematical equations, specifically the Navier-Stokes equations that are being solved in order to get all this magnificent visual representation. Okay, so let's have a look at some of the CFD applications. I think by now we are quite familiar. We have so many applications that we can apply CFD to. For example, in automotive, we can have a look at the aerodynamics of a car. We can see the impact of the weight. If you see over here behind the car, the weight being generated and being faced by the car behind the first row of the car. And then we can see, for example, this is Tesla's pickup truck. Cybertruck. So we can see the aerodynamic of it, and then we can see the airflow basically of a car, basically a sports car or a normal car. And then in sports, you can have a look. This is a golf ball. So this shows a comparison, interestingly, a golf ball without the dimples, okay, the concave shapes on the balls. So without and with the dimples on the golf ball. So the purpose of the dimples is to enhance or to increase the turbulence in order for the ball to go further. So we can see that by using CFD, we can see the impact. Okay, how many dimples are needed? How big of the design of the dimples are needed in order to improve the aerodynamics of the golf ball, for example. In cycling and in swimming, for example, if they are designing a new swimsuit, we can have a look at the aerodynamics of it in the water, as well as, for example, if a designer is trying to design a new helmet to decrease the drag on the cyclist, for example. Okay, and related to my field, this is an example of the use of CFD in marine or fluid structure interaction. So what you are seeing here is the simulation of a flow in between two land masses. So this is like a strait or a channel, okay? The inlet and the outlet here, which is impossible to replicate in a lab because this involves uh, a distance of hundreds of kilometers. So CFD can simplify that. So instead of conducting time-consuming and also expensive experimental procedure, we now can use CFD to see the phenomena and in research purposes, for example, to identify the location where we can deploy the tidal turbine, for example, for energy extraction. Okay, but again, remember, garbage in, garbage out. In order for us to get a simulation output like this, a clear, a high quality, and dependable result, then you must know what you're doing, what the input basically represent. Okay, so why we need to use CFD, or why use CFD in our life? Okay, as a future engineers, we need to have an answer for this. We need to have an understanding of this. Okay, so um, so before we go to this question, let's go back. So CFD, interestingly, cannot stand on its own. It must be supported by either pure experiment or pure theory or analytical analysis. Okay, because the result, again, the output from CFD, okay, the highly dependent on the input, and the output, okay, must be validated either results from the experimental procedure or analytical output from pure theory. So it cannot sit on its own, right? So the question is, for this part, okay, at which design stage of that you use CFD in the examples that we discussed in aerodynamics of the car, for example, in marine application, okay? So the answer is early on during R&D stage, okay, before fabrication and manufacturing. Okay, so we want to reduce errors, we want to reduce flaws at the assembly line. We don't want to fabricate or manufacture a product only after the manufacturing process are done, then we notice the defect or flaws. So we do not want that because it costs thousands or millions of ringgit. Okay, so in order to reduce all the defects, potential flaws, we conduct CFD study. Okay, it's like similar to FEA basically. We want to reduce the possibility of failure, okay, the possibility of defect in our product. So we start early on. Okay, so the other part, okay, when CFD is needed, because when the system is difficult to test or to investigate. So as I showed just now in this example, it's almost impossible for us to conduct this at a lab scale punya experimental procedure because this is a large scale modeling and the real place basically is not meters but in kilometers, hundreds of kilometers in size. So it's almost impossible to replicate in the lab setting. Okay, and the other reason why we need CFD to quickly test the answer of what if. What if we increase the number of dimples on the golf ball? What if we reduce the size of the dimples? What impact does it have? So because the output from CFD usually is faster, easier, and actually cheaper than the experimental setting. Okay. And the other reason basically is in entertainment. So, for example, if you're a fan of the Pirates of the Caribbean, um, and if you're seeing something cool like this on telly, anything that involves fluid, okay, air, fire is a fluid basically because it's air. Basically, the medium is air. Okay, so anything that involves fluid can be represented by CFD or can be used to solve by using CFD. Okay, all the cool effects that you are looking here right now, it uses the basic of CFD. So if you look over here, that's the Navier-Stokes equations. So this guy is among the first that use CFD in the movie animation, basically. Okay. So as I mentioned just now, if we want to compare CFD against experimental investigation or theoretical or analytical investigation, these are the pro and cons. Okay, so in experimental investigation, usually for full scale, it is often impossible. It's very expensive. Okay, and it usually comes with measurement error. So the tolerance, you have to consider that. Okay, but for example, the tidal turbine, okay, instead of 25, 30 meters long, we're going to do a scale model. We can do that for the scale model, but usually the physics of it is oversimplified. Okay, and again, it involves measurement error. So we cannot replicate 100% of what is happening for a large scale model against the scale model. As for the theoretical investigation, usually it's almost impossible to solve the complex numerical solution. Okay, so the solution only exists for a few cases, and most of the time it's very, very complex. So, and that's how basically CFD comes in. As I said, CFD alone cannot solve or cannot be the solution for all. It must be supported by analytical work as well as experimental work. All right, so just to give you a perspective, this is the blade for wind turbine. I've had the experience of seeing the blade being transported myself. It's seriously a logistical marvel. The way that they have to arrange for the transport is amazing and it's huge. So just imagine if we want to conduct a lab test for this, okay? It's going to be time consuming, it's going to be cost consuming as well because of the scale of the size or the object that we are looking at right now. Okay, so the pro and cons, okay, we discussed a bit just now. Okay, so in summary, basically, CFD, as we explained or discussed early on this lecture, when you look at the pretty pictures, a complex visual, nice to see, but behind it, basically, okay, behind the pretty figures, it all involve the physics, basically, the mathematics of it. Okay, so we have to understand the figures doesn't come out magically. It involves all the mathematical formulation as well as the physics that we learned back in high school as well as in the first or second year. Okay. Okay. All right. So again, to emphasize, CFD basically it starts from the governing equations, which is the Navier-Stokes equations. All right. So in Navier-Stokes equation, there are three governing equations that are important that needs to be solved, which are continuity, momentum, as well as the energy equation. Okay. So continuity deals with mass conservation, momentum in regards to F equals to ma, Newton's second law, and conservation of energy. So you don't have to worry. This is an introduction to CFD. We are not going to do this in the lab. Okay, so you can uh, stop your worry right now. Um, the details of this is covered in elective course in year 4. So if you're interested, you can take the elective course. But for the lab, we mostly involve the hands-on application, how to use the software. But as I said, before we use something, we need to understand what's behind it. And that's the purpose of this lecture, just to give you a brief understanding all the output that you get from your software. And I, in this case, we are going to use ANSYS Fluent for our lab. All the results basically comes from a set of governing equations behind the software, something that you cannot see, but you know that it exists and it is crucial and it is integral in the software in order for you to get the output. Okay, so just introduction a bit on the black box, okay, in order for us to understand better. So just assume that the tools that you're going to use, ANSYS Fluent or any software, is the black box. Okay, so that's the simulation tools. Okay, so in this case, assume that's the ANSYS Fluent that you're going to use in your lab. Okay, so we have a user input. We have some processes in there, right? And then you're going to get the colored pictures or the amazing visuals that we discussed just now. Okay, so it's important to understand the garbage in, garbage out analogy. How do you know the output that you have over here is okay, is acceptable, is reliable, is robust? That's the question that you need to answer. Okay, so the issues here, as I said, garbage in, garbage out, is that most users do not understand what is happening over here. And that is a big, big problem. Okay, so we need to understand in the black box, okay, the physical problem means the real phenomena that we are trying to investigate or to understand. So let's take one simple example, aerodynamics of a car. Okay, if you are designing a supercar, you want the drag to be as low as possible, for example. So that's the problem, the physical problem that you want to investigate or to solve. So this physical problem must be represented by a set of mathematical model. So if you remember the quote from James Clerk Maxwell just now, almost everything in this life can be represented or can be resolved, can be solved by using a set of equations or a laws of numbers. Okay, so we have a few assumptions, we have physical principles, and then we have to solve the mathematical model. Then we get a bunch of nodes, okay, which I'm going to explain in a bit in either in this lecture or in the lab later on. So in CFD, similar to FEA, basically you're going to see your object being split into several nodes or elements, and the result is being calculated at each of the elements of the nodes, basically. Okay, so after that, okay, so for example, these are the nodes. Then, as you get the result, okay, for post processing, once you get the result, you need to validate the result. Always remember, validation is very, very important in CFD. So you cannot just believe, okay, I already have the result. It looks great, so this should be correct. So I think that's a very, very dangerous assumptions, because all CFD results must be validated with some form of data, either by hand calculation, analytical, or experimental data. So you cannot run away from these two. Okay, so that's a bit of basic understanding of CFD, basically. Okay, so this is the summary of black box. Black box is the tools that you are using. So as I emphasize again and again, you need to understand that there are processes happening within the software. So the figures, for example, doesn't magically appear like this. Okay, so the question is, how do you verify that? Okay, how do you verify that this result is okay or not okay? I think that's the questions that you can learn from this lab that we're going to do in week 8 until week 10 soon. Okay, all right, so that's all for the introduction. and um, we're gonna start with the introduction to CFD procedure in the next video. Okay, thank you everyone for your time. Okay, I'll see you next time. Assalamualaikum and very good day to everyone.